In 2024, British Airways shocked the aviation world by grounding 6 of its Boeing 787 Dreamliners and suspending routes to Bahrain and Kuwait. At the same time, Wizz Air, a leading aviation analyst, predicted that 47 Boeing 787s would be out of service over the next 12 months. That's nearly a tenth of the global 787 fleet sidelined at any given time, enough to disrupt schedules, delay routes, and cost airlines millions in lost revenue. But here's the twist. All of this chaos comes down to one engine type, one single design problem that has rippled across the skies for a decade, reshaping airline operations, fleet strategies, and even long-term aircraft orders. Travelers might notice canceled flights or reduced service to key destinations. Airlines face the high-stakes puzzle of juggling grounded aircraft, maintenance delays, and operational costs. So why has a single engine caused 10 years of headaches for carriers worldwide? And how has it changed the game for 2 of the world's largest aerospace manufacturers? In this video, we're going to uncover the story behind the Boeing 787's troubled engine, the airline decisions it forced, and the broader battle between Rolls-Royce and General Electric that's reshaping the skies. Back in 2011, Boeing introduced the 787 Dreamliner as the future of long-haul travel. Lighter, more fuel-efficient, and packed with the latest technology. Airlines had a choice of 2 engines to power this new aircraft, General Electric's Gen X or Rolls-Royce's Trent 1000. At first, optimism was high. About 32.9% of airlines chose Rolls-Royce, while 53.3% went with GE. The Trent 1000 promised cutting-edge efficiency and the prestige of a Rolls-Royce power plant, an engine many carriers trusted for decades. But by early 2016, cracks began to appear. Literally. Corrosion, fatigue, and cracks in the intermediate pressure turbine blades forced Rolls-Royce and airlines into a crisis mode. At one point, 44 aircraft were grounded worldwide, and the financial hit for Rolls-Royce topped $1.3 billion. What was supposed to be a symbol of innovation turned into a maintenance nightmare. This was more than a technical hiccup. It was the beginning of a decade-long struggle. The Dreamliner's advanced materials and engineering, combined with the Trent 1000's design, created unforeseen challenges that would ripple across fleets, influence airline decisions, and ultimately shift the competitive balance in the aviation industry. The problems with the Trent 1000 engine weren't just headlines in trade journals. They hit airlines where it hurts most operations and revenue. Norwegian Air, for example, blamed these engine issues when it decided to exit long-haul operations entirely, a move that reshaped its business strategy and cut flights for thousands of passengers. Virgin Atlantic's CEO, Shay Weiss, went further, calling the situation a 10-year crisis, a decade-long saga of delays, cancellations, and costly maintenance. British Airways had to reduce capacity on routes to Doha, delay new services to Kuala Lumpur, and even cut flights between London Gatwick and New York JFK for several months. Air New Zealand suspended its Chicago route because it simply didn't have enough spare Trent engines to keep planes flying. Each grounded aircraft meant lost revenue, disrupted schedules, and frustrated travelers. A stark reminder that even high-tech engineering marvels are only as strong as their reliability. This wasn't an isolated problem, it was a global headache. The numbers tell the story of airlines scrambling to adjust their networks, passengers missing flights, and fleets underutilized, all because of an engine that couldn't meet expectations. The Trent 1000 crisis transformed from a technical issue into a strategic challenge, forcing carriers to rethink long-term fleet planning and route strategy. As the Trent 1000's problems persisted, airlines began rethinking their engine choices for future aircraft. By 2024, the shift was dramatic. 92% of new Boeing 787 orders favored General Electric's Gen X engines, leaving Rolls-Royce trailing far behind. This wasn't just about preference, it was a vote of confidence in reliability, efficiency, and predictability. Air New Zealand, for instance, had operated 787s with Trent 1000 engines but chose GE's Gen X-1B for its new orders. Similarly, Japan's ANA switched to GE for incremental 787 deliveries, signaling that even the engine's launch operators were losing faith in Rolls-Royce. The Gen X wasn't perfect, but its performance metrics spoke volumes. 1.4% better fuel efficiency on a 3,000 nautical mile mission, 3 times longer time on wing, a 99.98% dispatch reliability rate, and higher annual utilization. In practical terms, airlines could fly more often, spend less on maintenance, and keep schedules predictable, a critical advantage in a tight margin industry. This shift reshaped the 787 engine market. Rolls-Royce went from being a trusted option to a cautionary tale, while GE solidified its dominance. The lesson was clear. In commercial aviation, reliability isn't just technical, it's strategic, influencing billions in aircraft orders, airline planning, and the long-term health of an aircraft program. Facing a rapidly shrinking market share, Rolls-Royce knew it had to act, and fast. The company committed £1 billion to improve the Trent 1000, focusing on durability upgrades and redesigned turbine blades to resist the corrosion and cracking that had plagued earlier models. The goal was clear: restore confidence among airlines and extend engine life, giving operators a reason to stick with Rolls-Royce for future orders. Even with these improvements, the operational reality remains challenging. Out of all Dreamliners in service, roughly one-third still fly with Trent 1000 engines, but that share is steadily declining as new aircraft arrive with GE's Gen X engines. Airlines now weigh maintenance reliability as heavily as fuel efficiency or initial cost when selecting engines, and trust, once lost, is hard to regain. Rolls-Royce's efforts are a race against time, both to prove the upgrades work in the field and to convince carriers that the brand still represents quality and dependability. This section highlights a critical point. In aviation, engineering fixes alone aren't enough. Market perception and confidence can determine the fate of even the most iconic engine manufacturers. The Trent 1000 crisis didn't just hurt Rolls-Royce. It created a complex problem for Boeing as well. The 787 program was designed to give airlines flexibility, allowing them to choose between GE and Rolls-Royce engines. In theory, this should have been a strength. In practice, it became a source of tension. Airlines overwhelmingly favored GE, signaling a lack of trust in the Trent 1000. For Boeing, this preference matters. When one engine consistently underperforms, it affects customer confidence, slows new orders, and complicates fleet planning. Airlines are less willing to commit to aircraft powered by engines they perceive as unreliable, which can ripple across Boeing's production schedules and financial forecasts. The challenge is strategic. Boeing must maintain the promise of choice and reliability while managing the market perception that one engine option is inherently riskier. This situation also highlights a broader lesson. In aviation, the aircraft is only part of the story. Engine reliability drives operations, scheduling, and ultimately airline profitability. A single technical failure can influence the decisions of global carriers and shape the competitive landscape between aerospace giants. To understand how market preferences shape aviation, it helps to look at another story: the Airbus A380 versus Boeing's 7X, or Trip 7X. The A380 was a marvel of engineering, a double-decker giant capable of carrying up to 853 passengers. Airlines like Emirates, Singapore Airlines, and Lufthansa eagerly placed orders, dreaming of high-capacity hub-and-spoke networks. But the reality was harsh. The A380 required 4 engines, special gates, reinforced runways, and burned roughly 3,000 gallons of fuel per hour. To break even, airlines needed to fill 400 to 500 seats on most routes, a tall order for many markets. In contrast, Boeing's 7X, with just two GE9X engines, could carry nearly the same number of passengers on high-demand routes while using less fuel, lower maintenance costs, and standard airport gates thanks to its folding wingtips. By 2015, airlines had figured out the economics, efficiency, flexibility, and frequency mattered more than sheer size. Emirates began redirecting orders from the A380 to the 7X, and other carriers followed. The Super Jumbo era ended not because the A380 was a bad aircraft, but because it required a business model that most airlines couldn't sustain. Boeing's 7X succeeded by giving airlines the tools to be profitable, adaptable, and efficient. A lesson that mirrors the Trent 1000 crisis performance and reliability ultimately drive market decisions. The story of the Trent 1000 engine is more than a technical failure. It's a lesson in how reliability, economics, and trust shaped the aviation industry. A decade of operational disruptions forced airlines to rethink engine choices, fleet planning, and long-term strategy. GE's Gen X emerged as the reliable choice, while Rolls-Royce faces the ongoing challenge of restoring confidence in its products. Beyond engines, the broader lesson is clear: airlines prioritize efficiency, flexibility, and predictable costs over prestige or legacy. Boeing's 7X outperformed Airbus's A380, not by being bigger, but by matching the real needs of airlines: adaptability, lower operating costs, and route efficiency. The market rewards solutions that solve real-world problems, not just impressive engineering feats. Looking forward, the 787 program and GE's dominance illustrate how critical performance and trust are in aviation. Rolls-Royce's efforts to improve the Trent 1000 may regain some market share, but the lesson is permanent. Reliability isn't optional. It's the currency of global aviation. For travelers, airlines, and aerospace companies alike, the past decade shows that a single technical flaw can ripple across the skies, shaping aircraft orders, airline strategies, and the very economics of flight.